It's a big pleasure to be here, and I'm very excited to talk about you. I want to talk to you about this class of methods known as plug-and-play models. Who in this room is familiar with what it is? Yeah, so quite a big group who is somehow familiar with it. But what I'm going to try to explain you today is that it's a very elegant and mathematically rich way of integrating machine learning into the problems in imaging inverse problems. And then this is a reason that it kind of pulls me into it. But the second thing is, for anybody who's been following all the craze around diffusion models, there is also a very clear connection between that, because both of those approaches look at the idea of representing something we cannot easily get, which is probability distribution over images, by using something like a proxy. And in the case of plug and play, it's done through a denoiser. In case of a diffusion model, it's a denoiser by trained slightly different way. And we're going to talk about it today. Now, before going any further, let me say that it's been a while that I don't work anymore alone. So anything I'm presenting now has had a lot of contributions from very talented young people I work with. Who you see here are the members of Computational Imaging Group at Washington University. Every single topic I'm going to talk to has been done together with them, and then I would like to acknowledge their contributions to everything I'm doing. So it's not really an individual work. Now, to kickstart the actual presentation, the technical content of the talk, let me start by saying something obvious. We know that deep learning has been transforming imaging, including imaging at EPFL. But if you look at the pace of the progress, it's been just accelerating. It's not slowing down, right? If you go back 5 years, you might say, oh, it's a fluke, it's going to die in a few years. No, it's been keep on going, and we keep on getting new things that are even more impressive than the things that were before. So for anybody who has played with the model DALI 2, those are the ones you can see here. It's a model that combines a language model together with an image generation model, which is in fact a diffusion model. It's based on image denoisers. And it can do something like that. So for example, if you put it inside DALI 2, by the way, it's free to use. You can go online, log in and use it. It's called Oil Painting of Edison, Bribing Einstein in Newton's Garden Apple Trees During Rainy Day. You get this. Let's say I change a photo of Albert Einstein and Nikola Tesla playing Frisbee. You get this. A Steve Jobs eating dinner with Albert Einstein, 3D art. You get this. So there is one thing that's striking in every single example that you see here, is that every single image looks somehow realistic, meaning it's sharp, it's not blurry, it's not fuzzy. There are some issues. You can see it cannot deal with text and so on, but it's a remarkable thing. And this progress has been within last 5 years, okay? And now this year, anybody who has followed, we're getting even crazier with this thing. And anybody who's played with ChatGPT, you can get this. This is something I put on in an ITGV right to come here before. So here's write a poem about Computational Imaging Group at Washington University. That's what ChatGPT produces. You can look and get impressed how realistic this is in terms of its ability to combine the models we have for language to synthesize something that looks impressive. So today, my talk will be, in fact, very much related to this, but it will be all in the context of imaging inverse problems. But before getting there, let me just give a little pitch about computational imaging, because that's how I see my broader research area. So inverse problems for me are within the computational imaging area. So if you look at imaging as a traditional, history of imaging, originally it was all about a hardware exercise, right? You would try to map a point in somewhere in space to another point, usually in an eyepiece in a microscope or a film. You could record it and print it out. Then we got computers, so then we could have digital signal processing, digital image processing. I could now record the data from the instrument to a computer and do everything digitally. For example, deconvolve image, highlight image, do basic processing. Now we're coming to a third stage with all these things I just showed you, where now we're kind of combining two things. We have in the information coming out from the instrument, but we don't restrict ourselves to that data coming from instrument. They're usually data sets of external data, which might be from different modalities, different tasks, and different things that get aggregated into those machine learning models. So extract something that's not obvious in the data. So that's what I call hidden data. And that's I call it future, but it's really, you can see with the pace we see, it's a near future. And in the context of my talks, I'm going to talk about this for inverse problems, the way this kind of deep learning models can get integrated there in one particular way. So I put my talk into 3 sections. First, I'm going to introduce inverse problems in computational imaging, which I guess most of you are familiar with, but it will establish a common language for us to communicate. And then I'm going to introduce plug-and-play methods for inverse problems, which will be where I'm going to talk about why they became so dominant, popular, widely used. And finally, I'm going to talk about a version of plug-and-play that uses continuous representation of images, which is very recent work and I think quite interesting for many applications. All right, let's start with imaging inverse problems. So many computers, by the way, I love this slide. This is from Michael's slide. I have always liked the simplicity of it, so I always adopted it. So imaging inverse problems are quite common in computational imaging. The problem, if you understand it, is basically you have an image you don't have access to directly, but you have access to something else, which I called Y. So this Y is what I have, what I want is X, and all I have is some measurement of X through something that I know somehow, maybe exactly, or have some model about it, that A represents a sensing model, or some people call it forward problem. And another component is there's usually some noise, which is random, but we usually also have some idea what it is in the distribution sense. Okay, and the goal is to go back. We want to go to X given Y, which is something we've been doing for 100 years. It's a very classical area with a lot of development and still ongoing development in the area. Now, the reason I personally like imaging inverse problems is because it gives me a common language to address many problems. Okay, once you accept this formulation, now you can do innovations that can be applied to all kinds of applications. And if you go to my lab, usually in every single semester, we have 10, 12 applications going from traditional computational photography to bioimaging to medical imaging and so on. And this is a reason I really like it. Now, let me give you 2 examples for those who are not familiar. And those 2 examples will be running example through my talk. The first one is magnetic resonance imaging, which is pretty easy form. So easy meaning doesn't mean it's easy to do, but easy in the form of easy to conceptually understand it. It's a imaging modality where I don't, unlike photography, don't have directly access to the image. I actually can collect with this expensive machine Fourier space. So I can get frequencies of the image. And as I get frequencies, I can do inverse Fourier transform and get the image back, right? And then one thing you can notice is data collection is indirect and sequential. Okay, it's indirect, meaning I don't get the image directly. Sequential, meaning I collect frequencies one by one, which basically means there's direct relationship between the cost of data collection, maybe longer data collection, to imaging quality, right? And one way to do it, people who have been interested in, is try to keep the imaging quality to be diagnostic, but reduce the data collection so to increase the patient comfort. Okay? Now, this is an example of actually the real data we've been working on. If you would do a free breathing 3D MRI scan, so what you see here is a person breathing. As they're breathing, the body internals are actually moving here. This is a slice of the image. So there are 10 motion states here. If you try to cut it to 2 minutes and 1 minute, you're going to get something like this. So we don't want to do this because here I cannot see much to be able to do diagnostics. So there is a very interest to be able to get this form of images with this much time. All right. Now, the second application is maybe a little less familiar to many of you, except probably Michael, Dmitry, Psaltis, anybody who works with optical imaging, is intensity diffraction tomography, which is a different setup. It's a microscopy setup where there's a light source, which consists of LEDs. There's a sample, just 3D sample here. And then there's objective and finally digital cameras that collect. The way it works is you illuminate one of the LEDs. So for example, this one, if you illuminate the LED, the light goes through the object, gets collected by the optics, and finally you get an image like this on the CCD. And that's an intensity image that we get. Now, the nice thing is I don't have to take just one image. I can illuminate another LED. So for example, this one here. Now I have another LED and it gives me another image. So now I can get many images. So I could usually get hundreds of images. And for those who work with tomography or CT, this is very similar to limited angle CT. There is a range of angles I can collect with the device, except 2 things. First, the light object interaction is not based on straight rays because there is scattering. And the second thing is we collect the intensity of complex valued quantity. And the goal is, given this form of images, to use the knowledge of the light scattering to be able to reconstruct the 3D distribution of the refractive index, which means for every location inside the sample, I want to know a number. That number is complex valued. The real part usually tells us something about absorption of the sample, and the imaginary part tells us something about light scattering properties of the sample. The reason we want it is because if you look at refractive index, you can see the object, but also if you look at the values, usually you can know something about the material you're trying to image. So that's a reason we want to do. Now, it's very data intensive. You can imagine that we need to collect hundreds of those things. We have a limited angle tomography set up under light scattering and phase loss. So it's a pretty well-known challenging issues with a lot of work happening over the years. All right. So now let's talk about the classical issues in the context of imaging inverse problems. And those are the issues we're going to try to address with plug-and-play priors. So the classical issues that are quite well known, the first is acquisition is too slow or could be costly. That's I explained in the context of MRI. But the same is true for microscopy setups, because again, once you have indirect sequential imaging, there's a trade-off between time resolution and the spatial quality, so the image quality. So this is one challenge. The second challenge, reconstructed images contain artifacts. You can see it here. So this is a streaking artifacts in the radial MRI. This is a low axial resolution in the intensity diffraction tomography. And this is an interesting one. This is a CT of scanned luggage with angles being between -60 and 60 degrees. So it's a limited angle tomography. You cannot see anything in this case, again, artifacts, and we want to fix. And finally, high computational memory requirements, because we want to do 3D imaging, which means XYZ, 4D, XYZ time, 5D, maybe XYZ time spectrum, or you can imagine other kinds of quantitative parameters we want to extract. All right. All right, that was basically the language and setup. So now I'm going to go towards directly to plug-and-play priors to try to introduce you the idea of plug-and-play priors. So to introduce you plug-and-play priors, let me start out that plug-and-play priors methods, they build on a long-lasting line of work in the context of imaging inverse problems. By the way, anybody who is interested in this topic, there is a tutorial paper that's going to come out in IEEE Signal Processing magazine in January. Those are who are members of SPS. You will get it in your mailbox. Otherwise, feel free to go to the project page, get the paper and potentially the code. And that's the moment where my slides crash. Okay, good. I think somebody's camera interfered with my projector. Anyways, so feel free to look at my talk is really based on this work. All right, so let's start out with introducing the classical view of trying to solve imaging inverse problems. So anybody who's working inverse problems knows that imaging inverse problems are ill-posed. Okay, inverting that system is not possible without something else, which is usually a prior knowledge or regularization. So there are different ways to do it, but the one very common way is to adopt a Bayesian perspective. So what's a Bayesian perspective? I'm going to say, okay, this is my imaging inverse problem. What I'm going to say is that I know some statistics about the noise. I know my forward model. And then what I'm going to do is I'm going to actually introduce an image prior. Okay, I'm going to say we are not reconstructing anything. We're reconstructing something that can be, obtained from a lower dimensional subset of Rn. Okay, so it's a lower dimensional subset of Rn. But here's the challenge. We've been speaking about the fact that images live in a lower dimensional subset of Rn for a long time, right? But the question is, how do we represent it? So what kind of is it union of subspaces? Is it a manifold? It's very hard to know. There are different models. Different models gives us different trade-offs. But we know a few things. We know it's nonlinear because adding two images will not give you necessarily an image. And we know it's somehow lower dimension because we can compress images, right? And then the art is about trying to understand how to represent this. Now, if I would know the PX, then we can do a lot of things. We can, in fact, now take fully statistical perspective and try to design estimators. For example, I could design a maximum a posteriori probability estimator, which would simply take a negative log of my prior. If I know it, I can just put it in and do the optimization and get some image. Okay, but not only, I could even do MMSE estimator, which is basically conditional mean. So it's a estimator that maximizes signal to noise ratio, but it can also be in fact represented as a regularized least squares formulation based on a very elegant work by Gribonval, Mashach, and Nikolova. But both of those can be represented in this form. Now, a very special inverse problem formulation is image denoising. So here I represent the same formulation here, but for denoising. And you can see there's only one difference. We drop A. The A is set to identity. So if you set A to identity, so what are we doing here? We're trying to minimize the fit to the data. I want to make a maximum fit. And this is inspired from the fact that I'm assuming a Gaussian thing. And then we're trying to infuse a prior model. Here is the same thing. Now, I'm ignoring all the physics of my imaging instrument. So the formulation here doesn't have any knowledge of A. And it's actually known as a proximal operator. So if you look at the literature on optimization, this operation here, which is an operation that returns the minimizer of this thing, is known as a proximal operator. Okay? Now, essentially, the one way to think about plug-and-play priors, and we're going to talk about it in a second, is to build on a premise that the denoisers, which could be map or MMSE denoisers, are a convenient proxy for representing the prior on images. Okay? And it's convenient proxy from the algorithmic perspective. It's tractable. It's something I can do very easily. And once I do it, I can try to solve many, many problems. Okay, so that's the premise of plug-and-play priors. Of course, that comes with a lot of technical challenges. It's not as easy as just stating it, but that's was original motivation for the setup. All right? Now, let's bring the machine learning into this mix. So now I'm going to bring in machine learning. I'm going to directly talk about how to do this with machine learning. So if you want to adopt plug-and-play priors for machine learning, the way it goes is as follows. First thing we're going to do, we're going to try to learn a model that will represent our prior. How are we going to do it? We're going to simply train an image denoiser. Okay? It's an image denoiser that's going to take an image. I'm going to add additive white Gaussian noise. So it's completely synthetic noise. It's not, it has nothing to do with your physical model, your knowledge of your system. You might think my system is a Poisson noise. You might think my system is a blurred. You just ignore it. You're just going to add additive white Gaussian noise. And you're going to train a neural network to remove that additive white Gaussian noise. Okay? That's a first thing that should surprise many people, but that's a premise. The first part has no information about the physics of the sensing system. It's completely ignored. Okay? It's completely ignored. I'm training a denoiser. Now comes the second part. The second part, by the way, practically we also train a denoiser on several levels of noise, going from a low level of noise. 0 means it returns identity, so it returns the input. And then with more noise, where it starts smoothing more and more the image and introducing the prior. So we usually train denoisers with different levels of noise, with sigmas, from low to high levels of noise. And then once you apply them, you would get this kind of behavior. Now, the second component is we're going to bring in physical model. Okay, so that's separate. So the first part was denoiser. Now we're going to try to bring in something we know of the imaging system. One way to do is to say, oh, you know what? For example, if I know my noise is additive white Gaussian noise, I can write this data fidelity term, which is y minus ax squared. So it's least squares, which is fit for a Gaussian. And what I'm going to do, I'm going to just try to reduce it. Okay, I'm going to just go a step towards reducing it, which is this. So this thing is trying to take a gradient step, a gradient descent step, one step of a gradient descent to minimize this quantity. Okay, so what does this mean? This operation here I wrote goes from less measurement consistent to more measurement consistent, where measurements are y. So the x output of that step will be closer to y through the operator a. Okay, so those are the two operators, physical. And here's the deal. The whole art of plug-and-play priors, there are many versions of it. I'm going to show you one version, which is pretty easy to interpret. This is one easy way to integrate it. So this one comes from 2017 paper by Romano, Elad, and Milan Far, where they say, you know what, I'm going to write something like a gradient descent, except this is not going to be a gradient. But I'm going to have two steps here. The first step will do this. It's going to take me to be more measurement consistent. And the second step will try to get me closer to the fixed points of a denoiser, meaning input and outputs of a denoiser are the same. So when x equals dx, this is a fixed point. And we try to combine. In fact, we never usually get for this. So another way to rewrite it, you can in fact rewrite that whole thing in this form. And now you can think of it as a neural network. Now I have this thing, which is a gradient step with respect to data fidelity. And I have this step, which kind of tries to get output of the denoiser matched to the input of the denoiser. And you kind of put both of them, combine, and you run it, for example, for T iterations. You can think of it as T layers, or so it's a model. You can think of a neural network model that we do. Okay. So one thing I want to mention here, note, there is no training involved here so far. The training was done pre-training. You pre-train the denoiser. You fix the denoiser, you plug into this thing, and you run this thing. Okay, and that thing tries to find a balance. In fact, the fixed point of this algorithm, if you run it, x will be equal, xt will be equal xt minus 1 when this is 0, and this is 0, and this is equal to this. Okay, which means you're trying to balance the two terms. And tau here tells you how much importance you should put on this term in that balancing equation. So there's a nice connection to, traditional view on regularization with the regularization parameter and so on. But I'm going to give you more interpretation in a second. Any questions so far on this algorithm? So this is a plug-and-play method. There are many more. You can, for example, replace the step with a proximal operator of a data fidelity term. You can change slightly the way you're going to apply the denoiser. For each version, there are different publications trying to address it, but this is a version which I'm going to kind of run through today. Any questions? All right, so the premise is clear. Now, what it turned out is this type of methods have become quite influential in the past few years. And I think there are different reasons for different communities why they became influential. Because of certain mathematical elegance, you can do endless investigation of this kind of iterative methods, try to come up with their properties and things, relate them to neural networks. Flexibility, now you can swap this to different imaging models, right? I can use G for positron emission tomography versus MRI versus optical system and so on, versus D. You got a better neural network, just put that one in. You got a new neural network, just put that one in. There's some flexibility there. And final performance. Those methods lead to methods that can get us state-of-the-art performance in many imaging universe problems. All right? All right, let me kind of go one by one through some of those benefits. And I think this will communicate to you some of the properties of thinking in a plug-and-play way. So it's a way of, it's kind of a framework, how to look at the solutions of inverse problems. So the first one I want to talk about is actual empirical performance of those methods. So if I actually, well, let me put this here. So there are a few things you can know about plug-and-play priors directly by observing the algorithm itself. The first thing is they're not like generic. So if I look at this as a neural network, it's not like a generic CNN designed for blindly for a task, right? You can see it can incorporate information about physics, which gives it an edge. They're modular. I can easily accommodate most recent neural nets has become. And finally, there's one thing which is not obvious for many of you, probably, is that there's a term nowadays which is quite common. People call it implicit neural networks. What I mean is that you can run this iteration, the one I wrote, until it converges to some fixed point. You don't have to even run it to a fixed number of iterations, okay? Which means it can become a variable length neural network. You can think of it a variable length model. And sometimes it's called implicit neural network because now you can train those by implicitly differentiating using implicit function theorems, implicitly differentiating at the fixed points. Okay, we're going to talk about in a second. But the first thing to say is let me show you some of the different results you can get. So this is from ICML 2021. At that time, diffusion models were not yet the central thing. So the generative adversarial networks were accepted as state-of-the-art generative models. What you see is a method called intermediate layer optimization, which takes StyleGAN2, which is a very powerful generative adversarial network trained on celebrity faces, and uses it to do reconstruction from compressive sensing, meaning you take random measurements of this image, you keep only 10% of those, and you try to recover the image. Okay, so back in the day when I was a PhD student, this was an impossible task with the types of regularizers I used to use. Now with neural networks, it can actually become a reality with dropping 90% of those measurements. And then you can see that if you run a generative adversarial network, you're going to get an extremely realistic looking image. So, and then it's pretty accurate as well. So this number here you see is peak signal to noise ratio, which is like signal to noise ratio, but instead of the norm, you use the maximum value of the signal in the denominator. So higher is the better. This is another generative adversarial model-based method called Pulse from CVPR 2020. You can see ILO is realistically good. Now, here's the result of plug-and-play priors by training just the denoiser. nothing else. I train a denoiser based on a DN-CNN architecture, which is just a fully convolution architecture. Okay, there's no transformers in there, no GANs, and it does this. But you can see the drawback. It's actually smoother. You lose the sharpness, right? You can see, like, if you look carefully, despite the number being close, it's not as detailed here. You can look at the loss of features. If you look at another image, you kind of see it again at the different regions, that it's less sharp in terms of the same. And in fact, if you run a lot of experiments, you can see that usually plug-and-play priors is very competitive. I mean, very close to up to certain, but once you start to extreme levels of subsampling, if you just train a denoiser in a traditional plug-and-play way with someone else, it's not gonna be as good as or as realistic looking as using GANs. Okay. Now with diffusion models, by the way, this has been fixed, but that was the way it was back in 2021. Now, one way to do it, there's a very easy fix for this to improve the performance of PNP, but that will require us to step out a little bit. So plug and play, as I started, motivation is based only on denoising, right? Which raises eyebrows for many people. It says, you're doing denoising, but within the iterations of that, your artifacts are not additive white Gaussian noise, right? We're kind of being suboptimal. Can we do better? And in fact, you can do better by simply taking a more general perspective. You can say, you know what, I'm going to go from denoising to a more generic operator that I'm going to call artifact removal operator. That's going to remove artifacts specific to the intermediate layers of that model. Okay, so how can I get it? All I want to say, it's pretty easy to do, and that technique is to look at that iteration as a model-based implicit network specified through your choice of plug-and-play algorithm. So again, you can write this out. Now you can look at that fixed point of that algorithm, x bar. So this is x bar at theta. And you can pick recent line of work on deep equilibrium models where you say, you know what I want to do is have a run plug-and-play. I can initialize it with a denoiser, but I want to try to get a fixed point which gets me the lowest error or the highest SNR. Okay, so this is a loss function where x star is a ground truth. I'm taking one image, but if you have more images, you have a sum here. You have x star. X bar is just a fixed point of that iteration. Okay, you look at the difference of this. So x bar is a fixed point of this iteration. Now, in fact, by using implicit differentiation at the fixed point, you can write out the gradient of this. And if you write out this gradient, you can notice this term here. There's a negative inverse transpose, which can be also expressed as a fixed point iteration, which people call a backward iteration. Okay, so now you can think about it as a forward pass and a backward pass, where now you say, you know what, plug and play price is good, but I want to specify it to my system. Okay, I have my own imaging system. I want to specify it. I'm going to run until fixed point. I'm going to run it backward. I'm going to try to improve the SNR on that. And now if you do this, you're going to actually get realistic looking images, of course, that learn the now properties of the intermediate artifacts, which are going to be significantly better than additive white Gaussian noise, but also be extremely competitive with the GANs. By the way, here I'm showing you just celebrity faces, but if you look at the original paper, there's MRI, CT, and maybe intensity diffraction tomography experiments as well together. So the reason I picked here celebrity faces is because they're pre-trained models there. We don't need to retrain. We can just run those powerful models. And here, basically the gap you're going to get. So you can see this gap between GANs and the same architecture, but trained differently. So the training matters a lot, right? The way we train these models. All right, now let's move. So I said what I just said to you is that if you accept plug and play parts, you can get state-of-the-art performance and really better even than generative adversarial networks, the most powerful ones. Now the second one, and that's the reason I got into this, they allow you to get some statistical interpretations of the solutions, right? So let's talk about it. So if, as I said, you can start to interpret this kind of algorithms as statistical estimator under some mathematical conditions on the denoisers. And this has been a very active area of research. And once you have accepted, now you can do all kinds of fun things I'm going to show you, like sample multiple images consistent with the posterior probability, or look into theoretical insights on the robustness of those algorithms to the data distribution shifts and things like this. So there's a lot of interesting interpretations that can open up there. So let me show you this. So first thing to realize is a lot of the time we train our denoisers by minimizing L2 loss function. Okay, so what do I mean here? here I express the MMSE estimator for image denoising problem. So if you would write MMSE, it would be over all the set probability space of you defined. You're looking for a D here that minimizes the distance in L2 sense between X and the estimate, right? That's known as MMSE, so I put a D star. In practice, of course, we don't get D star, but our neural networks, when we use an empirical L2 loss, are essentially approximators of MMSE, given the ways a neural network can represent. So with the limitations of what it involves, but one way to interpret it as an approximation of this. But if we accept for a second that the D star is what I have, then I can do something very interesting. That was a very dramatic moment. I'm very happy. It's the right moment it played. But one thing you could do is if you knew you were using D star, which is MMSE estimators, then you can in fact prove that the plug and play algorithm using the MMSE estimator will have an interpretation as an optimization problem, where you have two terms, G and H. Okay, the H I'm not going to write it because it's a little not elegant expressing, but we know a few things. But we know that the algorithm will converge monotonically to a stationary point of this, where now HMMSE is very interesting. It's going to be not convex, not necessarily convex. It's not going to be the same thing as H-map, meaning negative log of Px, except in a special case of a Gaussian. And you can also interpret it as a map estimator of another distribution with exponential negative HMMSE. So this work here, in fact, builds on the Remy Gribonval's work I cited earlier. So for anybody interested in that, feel free to look into this. I'm going to omit all the proof. But all I want to say is that now you can start having this kind of nice interpretation of that algorithm I showed you, which is surprising, in terms of an optimization. But okay, now you can say, oh, wait, my D I use, a neural network, is not MMSE estimator. It's an approximation, right? I don't have D star. I'm actually a training neural network. Well, not a problem. If you do know that you have an approximation, you can bound that approximation error by something. You can just plug it into that algorithm, crank through the math, and find a bounds on your fixed points in terms of, so G star is the one fixed point of plug and play through D star. And I'm plugging XT generated by using a denoiser. That's a bounded error from it. You can see it has two terms here. The first term goes down to 0 as number of iteration layers kind of goes to infinity. The second term is fixed, but it depends on a sigma level and so on. But anyways, it's a bounded thing. Now, here's the pitch, what I want to say with this equation. What this means here is something surprising. Even if you train an MMSE denoiser, which can be potentially expansive, doesn't be a proximal operator or non-expansive operator, you can interpret it as MMSE. It can still be an expansive operator, but you can have some stability guarantees on the solution computed with a potential expansive operation. So you don't need this non-expansiveness of proximal optimization necessarily to have something stable. Of course, you don't converge because there is an error bound here. There is an error bound, but that explains why if you run any plug and play algorithm, there is kind of decrease and it kind of jumps around at some neighborhood of a solution. That's one interpretation I'm going to give. All right, and another thing now, once we have this, now I can do all kinds of fun things. Right now I know I'm approximating MMSE estimator. I have a statistical interpretation. I have a prior. I'm assuming that my DX, a proxy for my PX that I don't have. Now I can try to do something very interesting. Try to sample images from PX using D denoiser. Okay, and that's what I want to show you here. And then here, my denoisers are trained in a better way than we used to do. It's based on the diffusion models. And here's the thing. This is trained for limited angle scenograms with up to 60 degrees missing data. So I have up to 120 of missing data. We only collect 120 degrees. If I would do a filter back projection from there, that's what I would get. So this is a human body. This is a suitcase that I showed you. This is a suitcase. This is a human body. Look at all the missing information just because of all these angles that we missed. It's a heavily ill-posed problems. Okay, but now if I accept that and I run the denoiser trained at a lot of noise levels, I can create multiple samples. So here's sample 1, sample 2 of both suitcase and a human body, which look realistic, but could be wrong. And to convince you about that, this is actual ground truth corresponding to this suitcase. Look at this. It's trying to create this line here, but it's missing all that information. So it's missing all this information. So it's trying to draw something based on the prior, but this is how it really looks. Look at this one. Look at this one. It cannot get it. But here's the nice thing. I can generate hundreds of those images and try to plot the variance of all those images per pixel variance. What does this mean? Now, high variance means I have high uncertainty in that pixel. Okay, so it's clear that whatever you're missing will have high uncertainty. So if you look at the variance, you'll have places you're going to be missing a lot of information, which will be related to the things you're not reconstructing well with this algorithm. Okay, so, and this illustration for a 3D image. So you're going through slices of that suitcase. This is filter back projections. This is total variation for the same image. I mean, it doesn't work well because it's a heavily ill-posed problem. And this is the method using a denoiser within the algorithm. You can see it can get a very realistic looking images. This is just another example. And this is real data, by the way. This is really CT data from a suitcase data set.
So what you show on the right are cherry-picked samples or like some kind of average of them somehow? Like
it's very representative ones.
Okay.
Yeah, you can actually look. Eventually, once the paper is accepted, we're going to release the code and the data. You can look at it, but you know they're pretty representative. Again, they're not perfect. Don't mistake the fact they look good with the fact that they are exact. Okay, that's one thing we have to be careful. And you know, we're not. You know, I'm not a radiologist or a medical person in the sense that I'm a scientist who is exploring the potential limitations of this. I'm not advocating this to be used for cancer detection right now. Okay, don't jump on this and try to do this. We have to get guarantees, get more understanding of the problem before doing. But you will end up generating very realistic examples. So non-cherry picked realistic samples. Yeah. But and by the way, whatever this is based off training of a diffusion model like Mel, right? I mean, DALI is also not cherry picked. You can do it yourself. You can even run it, except OpenAI runs it on like hundreds of GPUs, which we don't do. We run it on fewer GPUs, but yeah, you can get that. All right, I'm going to skip this one. All right. And finally, there's one more thing I wanted to say is that just because we have an explicit separation between the prior and then the forward model here, the plug and play models are very easy to adapt to different sensing configuration and image distribution. What do I mean by this? If you want to calibrate something in your forward model, let's say you have a CT system with uncertainty, you have MRI with coil sensitivity estimates that you don't know, or you have optical imaging with transfer functions that are not exact, you can now combine it as an unknown, define priors on that, and to also do this kind of calibrations. And this is something I just going to briefly show. This is MRI reconstruction using automatically estimated coil sensitivity maps using the same architecture, basically the plug and play architectures that I showed you. Now, here you see the grappa. So for people familiar with it, and this is SSDU, means self-supervised deep unfolding method. So it's based on deep unfolding that gives this result. So calibration of coil sensitivities now can be part of that whole pipeline in a very easy way because data fidelity is kind of separated on it. And just to say a fun thing, as I work on the real data, this is my own head that you see here. So you can get convinced I do have a brain and it's there. And in fact, if I try to get a 3D face of myself, I would see something like that, which is from that MRI data. Anyways, so I'm going to skip this one to spend some time on the final part of the thing, because I think it's very interesting, which is going to slightly change. It's going to be still using, in fact, here it will be very interesting. We're going to look into imaging inverse problems in microscopy where I don't have any ground truth. So that will be formulation. So let me go this. So this is actually also a very recent paper. You can find the project. The code is online. There's preprint, and by now there's a paper is also already published, so you can find the full paper as well. And the code has also the data that we used for this experiment, so you can play with it. So the plug and play formulation I gave you is traditional discrete image model-based formulation. So what do I mean by this? I looked at the image as a vector where I have x1 through xn. So n meaning number of pixels or voxels you have. You predefine a grid. You put values on that grid. and then you reconstruct it by training a denoiser on that grid. Okay. Now, one thing that we could try to do is to go beyond the grid. Okay, to try to define something to be continuous. And what I'm going to talk about now is to try to use a coordinate-based neural network, which takes coordinates x, y, gives you a value at that coordinate as a way to represent the image. Okay, so now instead of getting the values on a predefined grid, I'm getting the weights of this neural network. Having the weights, now I can put any x, y's I want and synthesize the values at those. So now it becomes a continuous formulation of representation. But it's still data-driven. It's still data-driven, but continuous. Okay, I'm going to get there in a second. So the method I'm going to show you essentially decouples. It takes plug-and-play framework, but decouples the representation of the solution from any predefined grid. I want to be kind of try to, as much as possible, to decouple it from the grid. All right, and then we're going to test it on the intensity diffraction tomography. So the way we're going to do it, we're going to take a neural network, which is going to be coordinate-based neural network. Input will be x, y, z. So I'm going to put x, y, z as an input. For now, ignores this thing. And the output, I'm going to get two values, the real and an imaginary value of the refractive index. Okay. So for every x, y, z, in principle, I want to know the refractive index value. Okay. Now, the neural network itself will consist of two parts. Okay. The first part here is the easy part. It's a fully connected neural network that takes 3 inputs and gets 2 outputs. Okay, with the ReLU activations. Okay, so it's a fully connected neural network. Now, this part here, we adopted it from the work on NERF, neural radiance fields. So what this thing is, okay, ignores this visual representation. If you want the details, you can look. But essentially, it does a Fourier series expansion at XYZ of a function I want to get. Okay, so what does this mean? I'm going to predefine the frequencies for a Fourier series. And then I'm going to take X, Y, Z and just define the Fourier series. And the weight of each frequency will be learned because it's connected as a first layer of this neural network. Okay, that's the representation it's going to get. Okay. Now, this trick, we're not the inventors. Again, anybody interested, it's called neural radiance fields. It's been very well known in the context of graphics. But what we do, we adopted that architecture, and we're going to try to put it inside plug and play to do continuous reconstruction of objects. Anybody interested, I can talk about this more. But essentially, now we have image representation, which takes coordinate x, y, z, and tries to produce a refractive index. So now what we're going to do is we're going to define image formation as this kind of optimization problem where I have a data fidelity term, which will encode anything about the physics of the imaging instrument, and then the regularizer, which will have try to push me towards the fixed points of the denoiser. Now, the way we implemented this here is slightly suboptimal, and let me tell this, because A, in fact, is a wave equation. So whatever we implemented is based firstborn approximation anyways. But in principle, what's nice about this representation, because I have a continuous representation, I could try to do a better job in doing it. So I don't need to do it necessarily on a grid initially. I could differentiate this object with respect to X, Y, Z, and so on. But we didn't do it. What we did is we train it on certain predefined grid, but by passing X, Y, Z. But in the training, we do block coordinate algorithm, meaning because it's a huge sample, we just synthesize parts we need for the updates. So it gives us efficiency. But once we train it, now we can synthesize the object in a 3D by simply plugging in coordinates. And we can plug in coordinate with any density that we want. So I can plug in a 3.5x, 7.3, 31, because I do end up with a continuous neural representation of the object. And by the way, this allows us also to integrate nicely with optimization, because I can, if I have a wide field of view, it allows you to get a compression of the sample in 3D and 4D imaging. And what's interesting, it doesn't quite beat JPEG, but it can get quite close to JPEG compression. So I can talk more for anybody interested. But basically, now we have a representation decoupled from any grid, so images can be synthesized at will during optimization, and explicit and implicit image priors due to CNN, which is an image. I didn't say that. Image denoiser here was pre-trained with natural images. It's not trained with refractive index distribution. It's pre-trained with natural images. The only thing we're optimizing are the weights of MLP. So it's pre-defined denoiser in the regularizer. We're only updating the weights of the representation. All right, let me show you some real data solutions. Okay, this is a simulation. I'm going to kind of skip it for a second. So this is a real data. We have a bunch of other comparisons in the paper. So this is on a diatom algae sample. It's a 3D sample. So I'm going to go through the slices of the object and show you an image here. This is a traditional Tikhonov regularization. If you go to the paper, you can find also other regularizers, including neural network without continuous representation and also total variation. So if I would run this, you can see you get very nice representation of the object in the sense that you can recover very nice sectioning, optical sectioning effect. So we go through the samples here. And again, the flexibility here is that I can synthesize it at any upsampling rate that I want at will. I can pick any region and synthesize it. Here's another sample, buccal epithelial cell sample. Again, if you go through, you can see how sharp the images can be in terms of the performance of the algorithm. It's a really well-working algorithm. Here we actually synthesize all the slices that we didn't use in training. So in the well, I'm calling it training, but it's a reconstruction of the weights of the representation. You can see it's -54535. Those are the ones we didn't use in there. You can really get, here's the one as well. You can get very high quality slices that you reconstruct. Okay, and I think that kind of brings me close to my time to leave some space for Q&A. So I tried to, in my talk, to give two things. I tried to introduce intuition begin plug and play priors for those who are not very familiar with it, by explaining what their performance, trying to explain what kind of statistical interpretations you get and what kind of flexibility it offers you. And then I presented a recent result which tries to combine plug and play priors with continuous representations of the objects that we want to recover through fully connected neural networks. Okay, and at this time, I'm gonna thank you for attending this talk, and I will take the questions.